Hi everyone. In today's video, we're going to continue our discussion on alkynes, this time focusing on one specific reaction called alkylation and really harnessing this particular reaction in organic synthesis. This is, by the way, going to be one of the most important organic reactions you've learned in this semester, as this is the only reaction we've learned in organic chemistry so far where you can extend a carbon-carbon chain. Okay, so let's begin our discussion on the alkylation of terminal alkynes. So recall that if you have a terminal alkyne and you place that terminal alkyne in the presence of sodium amide, which is a really strong base, the terminal alkyne CH is going to be deprotonated to form this alkynide ion. And this alkynide ion is actually a very strong nucleophile and a strong base, which means that in the presence of a primary alkyl halide, this alkynide ion is going to engage in an SN2 reaction to form an internal alkyne with an elongated chain, now with an additional 2 carbons in the carbon chain. And this is what we call an alkylation reaction. Note that because this is an SN2 reaction, it actually follows SN2 rules, which means that you can only do this with methyl or primary alkyl halides. If you place this alkynide ion in the presence of a secondary or tertiary alkyl halide, an E2 reaction will occur and you will form your alkene. And so the generic reaction for the alkylation of an alkyne is you take a terminal alkyne, you react that first with your sodium amide in ammonia, which would deprotonate that terminal CH group. And then you can react that with an alkyl halide to then extend that carbon chain and you would form an internal alkyne. And just a quick note on this, acetylene itself can be alkylated, but it has to be alkylated in two sequential alkylation reactions. So for example, if you wanted to start with the acetylene on the left-hand side and form this alkyne on the right-hand side, you can go through two successive alkylations. You can start with your acetylene, react that acetylene with sodium amide, you form your alkynide ion. Note that only one side of this alkyne is deprotonated because it is very energetically unfavorable to deprotonate both sides of the alkyne to form a 2- species. You can then react this alkynide ion with the alkyl halide with the carbon chain on one side of your product alkyne. So this time we're using an ethyl iodide, and we're going to get this particular alkyne through an SN2 reaction. So you can then react this terminal alkyne with sodium amide again. You form your alkynide ion once more. And then once more, you can then react that alkynide ion with another alkyl halide, this time represented the number of carbons on the left-hand side of this particular alkyne product, which is your methyl iodide. And then you would form your internal alkyne. Okay, so you can actually do this again, once again, in two sequential steps. You can't do it all at once. And so in summary, here's a strategy for alkylating an acetylene on both sides of that acetylene carbon-carbon bond. So you first start with your first set of alkylation reactions to put an R group on one side of the acetylene, and then you can then do another alkylation to put the other R group or the same R group on the left-hand side or the other side of the alkyne. So you can essentially get a much longer alkyne using acetylene as your building block in your organic synthesis. Okay, so this is really it for your alkylation of terminal alkynes. It's really important that we realize that in your alkylation reaction, we've actually introduced a new form of synthetic strategies, which in this case is actually increasing your carbon-carbon bond chain. So now you can see that you can very readily increase the length of your carbon-carbon chain by simply forming a terminal alkyne and then alkylating that terminal alkyne. So as we continue to proceed with this class, we're going to learn more and more about how to use all the reactions we're learning together in organic synthesis. So in this particular part, what I want to sort of bring together here is how you can go from an alkane to an alkene to an alkyne, and you can interconvert between these three. Okay, so you what I have drawn here is an alkyne on the left-hand side, an alkene in the middle, and an alkane on the right-hand side. So we learned earlier on that we can convert from an alkene to an alkane using hydrogen in the presence of a platinum catalyst. We can convert between an alk we can convert from an alkyne to an alkene using H2 in the presence of a poisoned catalyst, such as your Lindlar's catalyst. Or you can treat your alkyne with dissolving metal reduction, with your sodium dissolved in ammonia. And both of them will lead you to an alkene, just the stereochemical outcomes could be different based on the reagent you use. We can also convert directly from an alkyne to an alkane using hydrogen in the presence of a platinum catalyst. Now, we can actually devise a multi-synthetic step method of going from an alkene to an alkyne if we first react that alkene with bromine in the presence of a non-nucleophilic solvent. So this would then put your two bromine atoms on the alkene. And then we can do a double E2 elimination of a vinyl dihalide in the presence of your sodium amide, and then you would end up forming the alkynide ion. And then we can wash that reaction or that product in water. So recall that this is actually a very impressive synthetic way of going from an alkene to an alkyne through a series of indirect reactions. We don't yet have a method of converting from an alkane to an alkene, for example. However, in chapter 10, we're going to discuss these methods and incorporate that into our synthetic strategies. And then recall that both the alkenes and alkynes can also undergo addition reactions. It's important for you to remember that each of these different core circles in your synthesis maps can actually spread out. So now let's look at an example of proposing synthetic pathways. And so in this particular one, we're asked to propose a synthesis of the product on the right from the reactant on the left-hand side. So in this case, it's important to note something about your reactant and your product. Importantly, you should be able to spot that the carbon chain has been extended from your reactant to your product. And the only way we know how to extend a carbon chain so far in this particular class is the alkylation of a terminal alkyne. And so this means that our reaction had to have gone through an alkyne and then an alkylation step in order to extend this particular carbon chain by one. So let's approach this problem by looking at a retrosynthesis. So if you had this particular trans-alkene, or this is where you're trying to get to, recall that we needed to have gone through an alkylation at some point, which means that at some point, one of the precursors in this reaction had to have been an alkyne. Well, we already have an alkene, and that could definitely come from an alkyne. So you can imagine a particular reaction in which you could have started from the alkyne on the right-hand side and lead to an alkene on the left-hand side. But now we know that if you have an internal alkyne, that could have actually come from a terminal alkyne through an alkylation step, which means that at that position where I have placed that red dotted line, there could have been a synthetic transformation to bring those two carbon fragments together. And so that precursor of your internal alkyne will be your terminal alkyne plus the alkyl halide, where the alkyl group is the fragment that you've cut out. And so in this case, it's your methyl iodide. So once again, this is the step going in the synthetic direction where an alkylation would have happened. Okay, so now thinking about retrosynthesis, we're actually pretty close to the reactant. So we have an alkyne right now, but we need to get back to an alkene. And remember from our previous scene that you can actually go from an alkene to an alkyne via a vinyl dihalide, which is to say that a precursor to this alkyne could very well have been your vicinal dihalide that we're showing you right here. You can imagine a double E2 elimination to get you to that alkyne. And so this precursor can very well also be the alkene starting material. Okay, so in your retrosynthesis, you're kind of going backwards, right? Where you're trying to figure out a way to get back to your reactant from your product. But once you do that, you can then propose a forward synthesis. So in your forward synthesis, you start with that alkene, and then to form the vicinal dihalide, you simply react that alkene with bromine in the presence of a non-nucleophilic solvent. Okay, so you get your vicinal dihalide. You can form your terminal alkyne by treating that vicinal dihalide with your excess sodium amide. Note that this gets you to the alkynate ion all the way because you're going to go through a double E2 elimination as well as a proton transfer step. However, that's actually what you need because the alkylation reaction requires your alkynate ion. If you react your alkynate ion with your methyl iodide, you can then form your internal alkyne that's elongated by one carbon. So now we're really close to our product alkene. So now if you want to go from an alkyne to a trans-alkene, you have to use the correct reducing agent. In this case, it's going to have to be your dissolving metal reduction, so your sodium in NH3, and you're going to get your trans-alkene as your product. Okay, so once again, it's important to start seeing how these different types of reactions you've learned so far come together in your organic synthesis reactions. So it's important that you're able to practice these synthesis problems extensively. There's so many problems in the textbook that you can do. I would look inside the chapter of the textbook in the practice the skill and apply the skill problems, as well as some conceptual checkpoints within the chapter, as well as doing some suggested problems as well. Okay, so that's really all I have for this video. In this video, we've really introduced one main reaction called alkylation reactions, and that has opened up a whole world of synthesis that we're going to practice a lot further. Thank you so much for watching this video, and I will see you in class.